Perfect. Thank you so much, Ivan, for the nice introduction. I will get straight into it. Today's topic on our side is micro-LED technologies for quantum systems. And in this talk, I will hopefully explain a little bit how these two are connected. But at first, allow me to introduce QubeDot at first. We were founded in 2019. Based on 45 years of development, and we have a unique technology to process the gallium nitride material system. And we are nowadays a passionate team of 15 employees. And there's a difference from us, of course, to other bigger players, because we do quite some non-standard processes and think a little bit outside the box. And we do understand the indium gallium nitride material system. Customers can receive their customized micro-LED solution even in smaller quantities with rather short lead times. And if we talk about micro-LEDs, our basis and our roots are micro-LEDs. And on this slide, I shortly want to show you like two standard systems, which are mainly kind of the foot in the door first system to talk about micro-LEDs. On the left side here, we can see a system with 16 by 16 pixels with a standardized contact ring for different pixel sizes, pitches, and wavelengths. This system has a frame weight, so like not pixel to pixel, but really frame to frame of 170 kilohertz. And pixel sizes range here from 5 to 130 micron. Same systems exist as well with 8x8 pixels. Again, with standardized contact rings and different pixel sizes and pitches and wavelengths. And for example, in the video that's right now playing, it's in 5 micrometer pixel size, 5 micron gap, so 10 micron pitch, micro LED array. In this case here, modulated with 1 kilohertz from pixel to pixel to pixel. And of course, that's a bit too fast even for the slow motion mode of our installed camera. We talk here about the gallium nitride material system and the indium gallium nitride material system. So all the wavelengths from the near UV to green are working pretty fine. We have developed an epitaxy as well that allows us to shift the emitting wavelength from a red, for example, and 630 nanometers red to a yellowish color itself. And also these red micro-LEDs can be produced with a feature size down to 3 micron and different aspect ratios, as you can see it here on the top right corner. Other companies sell this as dynamic pixel tuning. For us, it's just a nice feature that we can additionally add. And now I shortly want to switch a little bit in your mind, how does a pixel should look like? So just some examples of emitting micro-LEDs here. Pixels can be of any shape. They don't have to be square or round. So a pixel can also be a long line like we see it here at the top right. Here we have lines defined with a width of 7 micrometers, but they're 5,000 micrometers long. And on the bottom right image, for example, we see like the QubeDot logo at the moment that is emitting. And this is 1 pixel. So again, a pixel does not have to be round or square. Also, a single letter can be a complete pixel with our technology. And where would you use something like this, for example, in information displays, where you have these special kind of emitting pixels, where such a pixel is a complete letter or a symbol. And this means that like in the viewfinder of a camera, there can be an off-axis display with like recurring symbols in the end. As I said, the roots in my case are the micro-LEDs and micro-LED industry. And on this slide, let us have a look at our general take on displays. For once, we do agree with the market research company Yole, that if you want to make micro-LEDs successful, you have to have very high efficiency single micro-LEDs if the die size is shrinked to the low single-digit micron regime. And for having a display, you need a very high transfer mechanism that's very fast and reaches, for example, and yield of 99.9999. And just to give you a very small frame of reference, I think most of you know these calculations. If you assume a 4K display and you have so a 4K display has like roughly around 24.8 million micro-LEDs. If you have a successful transfer rate of 99.99, you would still end up with 2,500 dead pixels. And that's nowadays not really acceptable, which here means that you have to have the production and then very high control, but also the transfer process as well has to be very, very fast and has to be completely under control. And now I want to address today's topic. So let's address the quantum systems aspect of today's series of talk. Specifically, I will address ion trap-based quantum computers. For ion trap-based quantum computers, for example, you need to integrate and combine a lot of different things. You need different photonic elements. Might it be VCSELs, might it be DFB lasers, might it be waveguides, might it be also emitting elements like LEDs. You have to integrate the overlaying electronics, for example, with the microwave circuits to be able to control these single ions. For example, you would also need to offer a fiber coupling interface, and all of this on an interposer, for example, through glass vias or through sapphire vias with a high thermal conductivity. So no single material system can do all the tricks and can fulfill all the requirements. And for scalability, we need a system size reduction, as we already know it from other technologies, for example, from modern CPUs. This means that you do need a hybrid on-chip integration or a chiplet design. Like on the right, I put an image here of a quite current AMD CPU in this case, where we all know that they're produced in a chiplet variation. And to produce this also reproducibly and fast, you need this fast and parallel element transfer and the connection. And similar to micro-LED displays or the chiplet design, you will also have challenges like this exactly in the quantum industry. How does this look like at QubeDot? We at QubeDot produce micro-LEDs and other photonic elements. We bump them. We transfer with the tools available from our transfer toolbox. So on the left side, you can see such an example for an LED die, in this case of 14 micron with a triangle contact configuration. And we perform and offer the so-called laser lift-off after bonding and the laser-induced forward transfer for directly transfer single photonic elements and bond them. This means either way you bond the whole chip in once beforehand and you get rid of the substrate, or you shoot single elements with a laser from your donor to your receiving substrate. And for example, this lift process is highly parallel and you can transfer millions of units per hour. There's one other thing that I want to mention. So we all, I think, agree at the moment that in the quantum industry, there is no golden way yet, and that there's not really standards regarding the die sizes, the contacts, for example, emitter sizes. But having some kind of standards would have huge benefits at the industry of all industry players. And for me as well, I just want to, I don't want to urge, but I would like to promote that, for example, in such a consortium like EPIC, we can define a little bit different interfaces, especially if you think later on also on process stability and like transfer rates. And on the left side here, we just showed, for example, that like, of course, on different die sizes, you can have different contact pad variations, for example, ready to transfer. Again, for this standardization and for this transfer, I shortly want to show here on the left such a bumped photonic elements wafer. You can expect around, depending if you use 4-inch or 6-inch wafers, around 100 million LEDs or photonic elements on a wafer, on a single wafer, with die sizes of 14 by 14. And these ones then, for example, can be transferred via lift to the receiving backplane. And it's how we transfer these 14 by 40 micrometer dies. And again, these are exemplary for all kinds of photonic elements. On the left side here, again, you see the cross-section from the focused ion beam to showcase a defect-free interconnect. And on the right side, you can see that with this transfer, it is allowed for a very, very small gap afterwards after placing the photonic elements. So if you would use a classical pick and place, it might be able to place the first ones, but at some point you would get into trouble if you already have a bumped surface. And especially if we have now here gaps of around actually 2 micron street width, that's at least challenging. And at the end, I shortly want to address the famous epic questions, which is, what can you do for them? I hope you grasp a little bit of it. So we can design and process LEDs, lasers, and waveguides, mainly in the indium gallium nitride material system world. We do produce application-specific interposers and receivers. We have some transfers available in our transfer toolbox. And we also work a lot on the assembly and interconnection technology. And what can you do for us? In the best case, learn about the versatile possibilities of QubeDot and this gallium nitride material system, and talk with us about needs and potential capability matches. Then I would be really grateful. And with this, I'm at the end of my presentation. Thank you.